We know that the signs of the principal curvatures k1 and k2, okay, they determine the shape of the surface at a point on the surface, okay. So what we know about this, if both k1 and k2, if both are positive or if both are negative, okay, then the point is elliptic point, right? And if one of them is positive and other is negative, or if this is one case, and if k1 is negative and k2 is positive, then it's going to be the hyperbolic point, okay. And if one is non-zero and the other point is equal to 0, okay, or k1 is equal to 0 and k1 is equal to 0 and k2, oh no, 1 is 0, k1 is equal to 0, k2 not equal to 0, k1 not equal to 0, k2 is equal to 0, okay. So in this case we get the parabolic point, and if both k1 and k2 are equal to 0, then they are the point is the planar point. This is what we know regarding the shape of the surface at a point on it based on the principal curvatures at that point, okay. So with the help of these things, we can redefine these elliptic points, hyperbolic points, parabolic points and planar points with the help of the Gaussian curvature, okay. So what that, if both are positive k1 and k2, and if both are negative, then what will be the Gaussian curvature? Gaussian curvature will be positive because it is the product of the principal curvatures, right? So if k is the Gaussian curvature, k is greater than 0 at the point P, then that point P is elliptic point, okay. Now if one is positive, another one is negative, then the product will be negative. So if k is less than 0 at the point P, then P will be the hyperbolic point, okay. If one of them is 0, then k will be equal to 0, the product will be equal to 0, and if both are equal to 0, then also the Gaussian curvature will be 0. So if the Gaussian curvature is 0 at the point P, then the point P is either parabolic point or planar point here, okay. So now we will prove that how the Gaussian curvature, it influences the overall shape of the surface in this result, okay. So the statement is, if S is a compact surface, then there is a point P on the surface S at which the Gaussian curvature is positive, it is greater than 0, okay. So we will prove this result. Let us define a map F from R3 to R by F of V is equal to norm of V square for every V belonging to R3, the vector V belonging to R3, okay. The norm square of the norm function, so F is continuous function, okay, F is continuous. Again, now it is given that S is a compact surface, right, F is compact. So this function F attains its maximum value at some point of the surface S here. So I can find a point P in the surface S where the function F attains its maximum value at this point, okay. Now let me consider the position vector of this point as P. So P be the position vector of the point P, position vector of the point P, okay. Then this surface, compact surface S, is contained inside the closed ball of radius norm of P, okay, and the center origin. And how is it? This surface S intersects its boundary sphere at the point P. It intersects the boundary sphere at the point P here, okay. Now we will show that. Now what is the Gaussian curvature of a sphere? It is 1 divided by the radius square, okay, and this sphere has the radius norm of P, right. So the Gaussian curvature of the sphere is 1 divided by norm of P square. Now we will show that the surface S has at least this much Gaussian curvature. In other words, we will show that this surface S is at least as curved as the sphere at this point P here, okay. So now to prove this, what we want to show? We want to show that the Gaussian curvature of this surface is at least 1 divided by norm p square here. So to prove that, let me consider gamma of t, a unit speed curve in S, and it passes through the point P. It passing through the point P when t is equal to 0. Okay. Then f of gamma of t, okay, when t is equal to 0, f of gamma of t has local maximum at this point, t is equal to 0. F of gamma has local maximum at t is equal to 0. So what is the condition for it to have local maximum, or if it has local maximum, then what it should satisfy? It should satisfy that d by dt of f of gamma of t is equal to 0, and the second derivative of this f of gamma of t should be less than or equal to 0 at that point, t is equal to 0. Okay, so now just we'll work out this. So it's d by dt of f of gamma of t. What is f? It is norm of v square for v here. So f of norm of gamma square is equal to 0, and d square by dt square is of f of gamma. Okay, let me rewrite it. Norm of gamma square less than or equal to 0. So d by dt, what is norm of gamma square? It is gamma dot gamma. This is equal to 0. I can rewrite this as d by dt of, okay, d by dt of gamma dot gamma, that is less than or equal to 0. So what is the derivative here? Using the chain rule, you will get it as gamma dot is equal to 0, and using this here, okay, gamma dot, okay, actually we get 2 times here, and 2 is taken this side, so it will become, so I'll rewrite it as 2 gamma dot, that is less than or equal to 0. Again, using the chain rule, differentiate it, and what do we get here? Gamma double dot plus norm of gamma dot square, gamma dot. So the norm of gamma dot square, it is less than or equal to 0. Okay, so gamma double dot plus what is norm of gamma dot? Gamma is a unit speed curve, right? Gamma is a unit speed curve we have taken. So norm of gamma dot square is 1. So plus 1 is less than or equal to 0. So at this is all we have worked out at t is equal to 0. So what we have? Gamma of 0, gamma dot of 0 is equal to 0, and here we have gamma of 0, the dot product with gamma double dot of 0 plus 1 less than or equal to 0. Let me call this as the statement T together, A together with this. Okay, now gamma of 0 dot product with gamma dot of 0 is equal to 0. What does it imply? Gamma of 0, what is gamma of 0? It is this P, the position vector of the point P, right? This is perpendicular to the unit tangent vector to S at the point P. Okay, so hence it will be perpendicular to the tangent plane of S at P. Okay, so gamma of 0, which is P, it is perpendicular to tangent plane. Tangent plane to S at the point P here. Okay, fine. Now let us consider the surface path sigma. Okay, the surface path sigma in the atlas of S containing the point P. And let us consider the standard unit normal. S be the standard unit normal of this surface patch. Okay, fine. Now as you can see here, this P is perpendicular to the tangent plane to S at P, so it will be parallel to the standard unit normal. So what will be N? It will be plus or minus P divided by norm of P. Okay, let us call this as the statement B here. Now again, coming back to this statement, what we have? Gamma of 0 dot gamma double dot of 0 plus 1 is less than or equal to 0. So I can write for gamma double dot of 0 by the statement A. Okay, this will be less than or equal to minus 1 divided by gamma of 0. Okay, so gamma double dot of 0 is less than or equal to minus 1 divided by gamma of 0. Gamma of 0 is P. So norm of P. Okay. So we know the formula for the normal curvature Kn. Okay, what is the normal curvature of gamma at the point P? It is equal to gamma double dot at that point, the dot product with n, right? If you remember, Kn is equal to gamma double dot dot n. Okay, so substitute considering n, which is here, plus or minus P divided by norm of P, and gamma double dot, which is less than or equal to minus 1 divided by norm of P. What do we get for Kn here? It is either less than or equal to less than or equal to minus 1 divided by norm of P. Okay, when will it be less than or equal to minus 1 divided by norm of P? When this value, this n, okay, it has positive sign, okay, and it will be greater than or equal to 1 divided by norm of P. And when will it happen? When this happens, when this is negative. So depending upon whether it is positive or negative, we have less than or equal to minus 1 by norm P or greater than or equal to 1 by norm P for the normal curvature of sigma at the normal curvature of gamma at the point P here. So the principal curvatures of sigma at the point P are either both less than or equal to minus 1 by norm P or both greater than or equal to 1 divided by norm P, because we have proved in the earlier class that the principal curvatures at a point are the maximum and minimum values of the normal curvature of all the curves on the surface that pass through that point. So they are also satisfying the same thing because normal curvature does it. Hence, if both are less than or equal to this, then if you take the product, that will be greater than or equal to 1 divided by this square. And if both are greater than or equal to this, again the Gaussian curvature will be greater than or equal to 1 divided by norm of P square, which is greater than 0 at the point P. So the Gaussian curvature is positive at the point